So we're interested in crystalline solids in this chapter. So we can take the crystalline solid category and break it down into 3 different groups based on what are the individual particles in that solid. Are the individual particles molecules? Are they ions? Or are they individual atoms? So if they are molecules, then we have a molecular solid. Molecular solids tend to have low melting points because what's holding the molecules together? Only intermolecular forces. So an example of a molecular solid is ice. Ice is individual water molecules held together by hydrogen bonds. If we have ions, then the composite units are formula units. The empirical formula for the ionic compound, the lowest whole number ratio of cations and anions. And those ions are held together by ionic bonds, which typically are even stronger than covalent bonds. And so these tend to have very high melting points. An example of an ionic solid is table salt. Atomic solids are just going to have individual atoms. So these are going to be elements for the most part. And we can divide this into 3 more subcategories. Non-bonding, where the atoms are just held together by dispersion forces. These are going to have really low melting points. And the only examples of these are solid forms of the noble gases. We can have metallic atomic solids. So here the atoms are metals, and they are held together by metallic bonds. The melting points here are going to be kind of all over the place. Some of them are low, some of them are high. And then we can also have network covalent solids, where the individual atoms are held together by covalent bonds. But this is different than a molecular solid because you don't have discrete molecules held together by intermolecular forces. You have atoms within the whole network that are covalently bonded to each other. So these are going to have very high melting points. And quartz is an example of this. Diamond is another example. So the next few slides here just mostly say what I've already said. This one's kind of interesting. Some molecular solids can crystallize in different structures, and these are called polymorphs, different shapes. They can have different melting points, different solubilities. Some of their other properties can always also be different. And this concept is really important in pharmaceuticals because a different polymorph might interact with biological tissue in a different way. So one polymorph might be beneficial, and one polymorph might be toxic or do nothing. So exactly how they're put together matters. Another place where this is interesting is chocolate. So cocoa butter has different crystalline forms. And what form you get depends on how hot you made it and how you cooled it down and a lot of different things. So there's actually 6 different forms or polymorphs of cocoa butter. The most desirable is number 5. The texture and appearance of these and the melting point is going to be different. So this most desirable one is nice and firm. It has a nice snap to it. It's going to be smooth and shiny, and it's going to melt in your mouth. So this is the best kind. Some of these other ones are like soft and crumbly. They'll melt in your hand. They'll have some blooming. What's blooming? Okay, so this is a good piece of chocolate, and this is a piece of chocolate with bloom on it. It kind of looks moldy, doesn't it? You ever found some leftover Halloween candy from like last year? You're like, ooh, chocolate, and you open it up and it's like, oh, ugh. There's nothing wrong with that chocolate. Okay, the texture might not be quite right, but it's not harmful. Okay, it just looks funny. It's just started blooming, that's all. Yeah, it's not going to be exactly the same, but I think it's still worth eating, personally. Anyway. Ionic solids, we're going to talk more about those in a minute. The atomic solids, the metallic solids, again, this is another illustration of that electron C model of the metallic bond, where we've got the atoms of the metal arranged in a lattice, and then the electrons are kind of swimming around free, and that's what's holding them all together. The network solids are kind of unique in that those crystal structures are going to be limited by the constraints, the geometry constraints of the covalent bonds. So remember we talked about orbital hybridization and how if you have 4 bonds, it's probably going to be a tetrahedral shape, whereas if you just had 2, it would be linear. And so the shapes here are going to be limited by those geometries, so they're not going to form closest pack structures. And very high melting points again because covalent bonds are really strong. Okay, so this is a kind of question you should be able to answer, and it's actually a lot easier than it seems. So what type of atomic solid is Au? Well, you want to ask yourself, what kind of an element is it? It's a metal, isn't it? So is this non-bonding, metallic, or covalent, network covalent? Metallic maybe, huh? Because it's a metal? Yeah. So this is a metallic atomic solid. The only non-bonding ones are the noble gases. If it's not a noble gas or a metal, then choose network covalent. Here's another question along those lines. Which of these solids would you expect to have the highest melting point? Well, what's holding these units together? This is an ionic compound, and so its solid is going to have alternating ions held together by ionic bonds. It should be really strong, high melting point. What's the unit here? Are those atoms? Ions? That's a molecule, right? What's going to hold the molecules together? Dispersion forces, because this one's nonpolar. Dispersion forces are pretty weak, especially compared to ionic bonds. And then what about this guy? That's just an atom, right?
Could be dispersion forces.
Dispersion forces also, right? So this is an ionic solid, this is a molecular solid, and this is an atomic non-bonding solid. So we would expect the ionic compound to have by far the highest melting point.
Noble gases can
Noble gases can form solids at extremely cold temperatures. I'm not sure if anyone's made a solid of helium because it boils at 4 Kelvin.
It's a liquid, right? Usually that's the lowest they've been able to get it is liquid.
I think so. But things like krypton, because they're much larger, their dispersion forces are stronger, and so they're going to have higher melting points. And yeah, you can have solid krypton. It just has to be super cold. Any
And that one's
questions?
still pretty close to absolute 0 too.
Well, yeah, it's going to be down there, I don't know, like 100 or something.
And
Yeah, it's still so super cold. Any questions?